All right, everyone, welcome to this month's Roman Community Forum. Today we're going to be hearing about the Roman Touchstone Fields. Before we do that, we're going to hear some project updates from Jeff. Jeff, you want to unmute yourself and share your screen?
All right, let's see if I can find the right window here. All right, and let me. So are you seeing the presenter mode or the full screen?
Looks great.
All right, great. So, all right, so I was looking back to when I last gave one of these, and it's been, I think, since late November. And a lot has really happened since then. So at that point, we had just taken delivery of essentially all of the last bits of flight hardware. And what we've done since then is put most of that together. I'll be showing some photos in a moment, but just to sum up, we've now integrated the wide field instrument, coronagraph, and the telescope onto the instrument carrier and did all the alignment checks, or at least those you can do at ambient. That's the thing we call the integrated payload assembly, which I mentioned because we're about to start combining acronyms. Late in December, we mounted that onto the spacecraft. That creates an acronym we call SKIPA. That doesn't involve any optical alignments. So that part was actually, well, lifting anything that big is a tricky business, but it was otherwise straightforward. In the ensuing 2 months, we've essentially been doing what we call electrical integration and testing. There are literally hundreds of connectors to mate between the payload and the spacecraft. And with each one, it's a pretty elaborate process for checking that everything in the harness is still okay. And then you actually test the interfaces between each element as you connect things. We have found a couple of issues in the harnesses and the process of doing that. So we've actually lost a few weeks in schedule as we sort through those, but that is, I think, pretty much done now. Other stuff that was going on in parallel is that we've integrated the outer barrel assembly, sun shield, and deployable aperture cover. That is going to be going into the thermal vac chamber next month, and that will be tested separately from the spacecraft and payload. We've also run what we call a Pathfinder test in thermal vac. The idea is you never do any particularly complicated exercise with the flight hardware until you've done some kind of dry run with some hardware you don't care about. And that was successfully completed. Then on the sort of programmatic side, we had the official review with the agency, giving us the approval to move into what NASA calls Phase D, which is Observatory Integration and Test. That's actually was chaired by the Associate Administrator, Jim Free, who just retired, but that gives you some sense of the level of attention the project gets at the agency level. From a practical standpoint, what that does is it releases the funding for us to continue for the next 2 years through launch. All right, from the project schedule, this is, I think, almost identical to the chart we showed in November. I meant to draw a little vertical line here. Where we are now has moved another month and a half forward. Everything you see on here is still essentially on schedule to proceed as shown here. I should also mention, I guess, the mission ops review, which is a ground system review, was held and passed back in December. So on to a few pictures. So starting here on the left, it's a little hard to see, but if you blow it up, you can actually see the connections of the crane to the telescope, lowering the telescope onto the instrument carrier. And then on the right is the completed payload with the telescope and the instruments all mated. That was a nice day, to say the least. And then moving on is when you pick up the whole thing and put it on the spacecraft. The picture on the left, again, if you squint, you can see the spacecraft behind the scaffolding. That was basically a whole day work to pick up the payload and mount it to the spacecraft. But that all went basically according to plan. And then the picture on the right shows the integrated payload and spacecraft bus. So it really is starting to look like an observatory. For those of you who have been watching, PowerPoint CAD drawings from me and others over the years, it's nice to see a real photo. Moving on, so the other piece is what we call the OBA-SAS DAC, the outer barrel assembly. Whoops. Deployable aperture cover. The photo on the left right now doesn't yet have the solar arrays mounted on it, but you can see what the deployed aperture cover looks like. They had just completed a deployment test there. The photo on the right is looking from underneath the outer barrel assembly out to the top. So that's what the primary mirror is going to see with all the baffles. On the left is a photo of now the solar arrays have been integrated to the outer barrel assembly. That photo was literally taken at about 7 o'clock this morning. Up until that point, that whole assembly had been horizontal, which is the orientation they had used to install the solar arrays. And that fancy fixture is basically used to rotate things between a horizontal and vertical state. And then the whole OSD was then down on the floor in the clean room, which of course was also taken this morning, probably about 10 o'clock or so. If you look really closely up here at the top, you can see several of the core sun sensors that are mounted on the top of the center solar array. So this is the assembly. It's going to be going into thermal vac, and I guess its own vibration tests and so on, starting next month. And then after the spacecraft and payload go through their own environmental tests, then this gets lowered down on top later this fall for the last stage of observatory integration and test. And then finally, here's just a view of the clean room this morning where you can see the outer barrel assembly and solar arrays, and then the spacecraft and payload. And then behind that is the outer barrel assembly simulator, which is actually quite a high fidelity simulator. That's what was used in the Pathfinder tests for thermal vac. And it'll be mounted on the spacecraft and payload assembly for its thermal vac test. So it's got all the same heaters and thermal sensors and everything else that the Flight 1 has, and that'll be used to basically provide a very high fidelity thermal environment for the payload during its testing. This is essentially the same schedule for the work of the core community survey definition and the ROTAC that Julie and I and others have been showing since, well, for the last 2 years, actually. And we are now basically almost all the way to the end of this. The ROTAC has been meeting regularly. They are due to provide their recommendations to us next month. So that's all keeping on track. And then the last thing, I just want to give a reminder that this year's Roses Call is obviously out. The deadline is next week. If you are submitting a proposal, you're probably well aware of that deadline, but I just thought I would take this opportunity to remind everyone. And that is all I had for mission status, but I will be happy to take questions. And sorry for the dog growling in the background.
No worries. All right, so you have some time for questions. You can do it either by writing your question into the chat and I can read it out loud, or you can raise your hand and I'll call on you to unmute yourself. Also, I just posted into the chat some really cool fall and winter 2024 hardware highlights that we just made public yesterday. So choose your social media platform of choice, and there's some really cool images of all the work that's been happening on Roman for the last few months. So we'll pause here and see if anyone has any questions at all. Well, I have one. Jeff, are those the SAS A or SAS B panels that are currently on the outer barrel assembly in the clean room?
Those are SAS A. Those are the flight panels.
Oh, super cool.
At least I think they are. Actually, that's actually a good question. There's not really much difference between them.
Ryan, yeah, go ahead.
To the best of your ability, has there been any issue with either schedule or with the funding related to what the current administration is doing?
There has not yet been any impact to us. We've not had any of our, well, almost everything is built. So if they were stopping money on a contract, that wouldn't affect any of that work. Of course, we have no idea what's going to be in whatever budget is finally passed for the year. I'll just say that in past years, even when the prior edition of this administration was proposing that we be canceled, that Congress always came through with our funding. If we have a government shutdown, that's a problem because basically every day we are shut down is a day for day hit on our schedule. So right now we have something like 60 days of funded schedule margin, but every day of a shutdown is basically going to eat into that. So that's actually the most likely source of difficulty for us. And that's like literally all I know at this point.
Thanks, Jeff.
Any other questions from Jeff at all? And then Julia, I see you're on the line. Do you have anything else you wanted to add as well before we turn it over to the next topic?
Nope, I think Jeff did a fabulous job. Thank you.
All right. Well, thank you, Jeff. Really appreciate that update. And then next, I'm going to give you permission here. And then just want to test out your audio really quick.
Yes,
Your screen, it looks great. Great, I can hear you as well. And next up, we'll be hearing about the Touchstone Fields report. So please take it away. Thanks again for having today's talk.
Thank you very much. Thanks for having me present this. This is not my work, certainly not only my work. There's a lot of people involved in this, and so I'll try to make sure that you all hear that. First of all, Touchstone Fields is a little bit of a funny name, but we have been using this name for over 5 years now. Basically, when we were trying to develop a calibration plan, we figured that it was a good idea to have some reference fields that we could go and visit over and over again to make sure first to choose them so that it would be accessible and useful, have useful sources in them, but also to revisit them regularly so you could make sure that the mission was remaining very stable. So basically, these are areas of the sky that have proper parameters of accessibility, target properties, specific objects if necessary, and are likely to be repeatedly visited by Roman during its mission for its calibration. There are multiple fields to support different types of calibrations. Not all calibrations involve touchstone fields. A lot of the Roman calibrations actually use science images directly, and some of them are just special purpose fields or targets that we don't feel necessarily need to be described as touchstone fields. But so this was part of the concept that we presented in the calibration peer review back in July 2021. It's almost 4 years ago now. And they're being revisited now in preparation for commissioning, but they're not just for commissioning. They're also thought of with an eye of regular mission activities. Now, this report that's almost completed, we are going through the last round of reviews internally for the calibration working group before getting a broader review, is the result of work by a lot of people in the calibration working group. Neil Zimmerman and I, who co-lead the calibration working group, have coordinated the effort. But there are 3 main sections with different leads. The photometry section is being led by Ben Williams. The astrometry section has been led by Andrea Bellini, and the spectroscopy section by Greg Wolf. And I believe Greg is on the audience, so if you have questions about spectroscopy, I'll probably direct them to him. I don't know if anyone else is here. But also there were additional contributions by Vivian Meta, Annalisa Calamida, Susana Dusto, Jeff Kruk, Mario Gennaro, and a lot of other people who I really can't name because I don't know everybody who contributed. But basically everybody in the calibration working group has had a hand either by contributing materials or reviewing the write-up. We also, and this is something we're very grateful for, got input from the Euclid mission, passed on to us by Misha Schirmer and others, who have told us about their experience and given us some very useful indications in planning where to look, essentially. Okay, just a summary, and after this you can go away and have a good rest of your day. But these are the 5 main calibration touchstone fields that we recommend for use in the during commissioning and during the mission. They're listed by the name, the location, the goal, which optical elements are used, and we also have an indication. This is an approximate indication of how long it will take to take the first observation. In many cases, we expect these to be visited again over and over, but maybe not all observations will need to be as long as the initial observation. Just briefly, the LFC astrometric field will be used for both photometry and astrometry. It's around near the bar of the Large Magellan Cloud, and will be observed with all imaging filters. A small region of the Kepler survey field will be visited also for photometry, especially with an aim at characterizing the chromatic terms, also with all filters. Then there is a planetary nebula. This one was identified, in fact, by the Euclid team that will be used for prism wavelength calibration. The prism wavelength calibration will use the Southern Beehive, most likely, which is an open cluster in the southern continuous viewing zone. And the Euclid Deep Field North is the primary target for relative flux calibration for spectroscopy for Grisman prism. Going over the 3 parts that I mentioned now one at a time. For photometry, we had a number of different goals. We wanted to provide the result of observing the calibration, the touchstone reference field would be to provide a uniform relative photometric calibration over the whole field of view of WFI with a precision of at least 5 millimags. To provide a uniform photometric calibration to better than that, to 2 millimags over scales of order of 100 arc seconds, 1,000 pixels roughly. So several such regions per detector, so that you can have better smoothness of the photometry on smaller scales. Characterize and correct for the photometric impact of bandpass variations to about 2 millimags, again over the instrument field of view. So it's all relative photometric calibrations, and also track the temporal variations of the photometric response to 5 millimags, or preferably 2 millimags, when averaged over the instrument field of view. And these goals need not be achieved fully during commissioning, but should be supported by the choice of the touchstone fields. So for the primary photometric field, we chose a field near the bar of the Large Magellan Cloud. This is an image of one such region. This is the field, the area extends from a larger region, but this is basically one of the nominal positions that we could have. This region has a very high density of stars accessible to Roman for accurate photometry. So we can get to signal noise of about 100 on tens of thousands of stars in 60 seconds. But it does not have a lot of very bright stars that could otherwise create trouble. It is in the Roman CVZ, like the Large Magellanic Cloud as a whole. It is shared with astrometry, so this actually is dual purpose, as I mentioned before. So I'll discuss the astrometry part later. And there will be a region of about 1.5 by 0.9 degrees, which will be covered by large emitters. Basically, the region twice the size of the field of view of Roman will be covered altogether. The orientation will depend on the launch date because that will give us the accessible roll angles. But essentially, any orientation is okay for this region. So although the exact pointing and the exact orientation will depend on launch date, we will have access to this region regardless. So the idea here is that we would take photometry of all the stars in this field using small-scale dithers to make sure that we do we properly fill the phase space or the pixel phase for each source. And we will do multiple observations of the target region. For photometry purposes, dithers will be up to 30 arc minutes. So basically, you observe a single source in many different locations in the field of view. The assumption is that the source is always the same photometric brightness during the process, and so any variations are due to variations in sensitivity or response of some sort. So it's a way to do a flat field without a sky flat field, but driven directly by photometry. In practice, we will use a data pattern that's slightly different from what we would have chosen for photometry because it's driven by astrometry, but it will work just fine. In fact, it's more than needed. There will be about 50,000 stars, which will be observed at high signal to noise at least 3 different detector locations. So below, you can see the luminosity function of this field of a region of about 1 degree radius in this field. And you can see how many stars there are available at a brightness of a 2-mass brightness of 15 or brighter. In fact, at about 13.5, you start having problems potentially with saturation. So the actual sources that are optimal for our purposes are slightly fainter. Go down to about 16 and a half, but this is just illustrative of the kind of information we will have. So with this kind of information, we've simulated the type of observations we will do, and we can obtain a nominal accuracy of better than a millimag on every 100 by 100 arc second region, even if you assume that each photometry point is not as good as 0.01 magnitude. So in fact, it will probably be better. The typical signal noise will probably be close to 200. And this part is only takes care of the gray response. Basically, there are no chromatic terms that can be obtained in this field, primarily because, as you can see, the range of sources is very narrow in color. So all the sources are almost the same color, not exactly, but there is not a lot of range in color. So it's hard to distinguish the response of a redder versus a bluer source because they're very similar. Feel free to stop me if you have questions, by the way. I'm happy to take questions anytime. So, but moving on to the chromatic terms. So as thermal vacuum is shown, and it was known beforehand, that the effective filter bandpass over the field of view of the wide field imager is pretty significant. That has been measured very carefully in TVAC. There is an analysis by Eric Schweitzer that provides essentially the change in the blue and red edge of each filter over the field of view that comes essentially primarily from a change in the angle of incidence of the rays, depending on where you are in the field of view. But this is based on TVAC observations, and we want to verify that the same type of information applies to on-orbit data, because they will have a slightly different pupil, there will be the telescope in front of it, etc. So for that purpose, we want a large-scale response characterization, but for sources with different spectral energy distribution. So we can make a comparison and see if essentially the color, the photometric corrections for blue sources and for red sources are the same. And if they're not, they need to be addressed and characterized and modeled. So for that purpose, we went to a different field, a region inside the Kepler survey field, which happens to also be in the continuous viewing zone, but in the north, and offers a similarly high source density, about half of the source density as the LMC field, but a very different spectral type from LMC sources. So just here you can see on the top is the color magnitude diagram for the LMC, which is pretty dominated by red giants and giant branch stars. And the bottom is for the Kepler field, which is mostly dominated by main sequence and younger stars. So for that reason, they're much bluer. And so if you combine these two fields together, they'll give you the information to match the photometry in different bands, and therefore to disentangle possible chromatic response variations over the field of view. So together, the LMC and the Kepler field will enable us to identify and characterize chromatic terms, verify, if you will, the ground-based model, or make small corrections as necessary to about 1 to 2 millimegs. And the ground-based observations are actually critical because they will not only provide a starting model, but also will help direct the analysis. So many thanks to everybody who has done the TVAC measurements and the analysis, primarily Eric Schweitzer. Okay. All right. Temporal variations, it's pretty straightforward. We have observations of these fields. We will just repeat them to either field. Depending on the accessibility, the details are going to be decided as part of the commissioning process that identifies and specifies the commissioning activities. But then also during the mission, we can revisit each field, and the revisits will not need to be quite as extensive. They are both the fields are in CVZ, so they're both accessible year round. We will probably only do a subset of dithers, shorter observations, but if we find a variation and we need to redefine or redetermine the flat field or the chromatic terms, we can decide to execute more detailed observations. The resources are there in terms of the information to do this if necessary. Now, this is true for all of these areas. There were also other fields that were considered if needed. Each of them has some advantages, but a disadvantage as well in comparison. So one was the Draco dwarf spheroidal satellite of the Milky Way that has bright sources, but with very low metallicity, so a fundamentally different spectral energy distribution in details, but the source density is quite low. The Euclid deep fields and the self-calibration field, which is part of the Euclid deep field north, can be used to cross-calibrate with the Euclid mission and provide also an additional potential source of information, but they also have fairly low source density. The source density is important because having high source density allows us to efficiently obtain much better flat field characterization on smaller spatial scales over the detector, because you just have much more multiplicity of information. The 30 Doradus field in the Large Magellanic Cloud has a high density of very young sources. So again, much bluer than the other fields, much bluer than the Kepler field as well. But it has somewhat structured background for emission from star-forming regions. So it potentially more difficult to obtain accurate photometry. And the fields have been used extensively for JWST and HST in globular clusters like 47 Tuc or Omega Sen, have a high density of sources, but the field of view of Roman is so big that as you observe one of these systems, the density of sources will change significantly over the field of view, and that makes any analysis and observation plan a little more difficult. So for all these reasons, we favor the first two options, but these are there and have been looked at if in case they're necessary. Let me stop for a second if there are any questions about the photometry part. If not, okay, let me continue then. The astrometry plan is basically, the goal is to determine the geometric distortion of the wide field imager to better than 0.1 pixels across the focal plane. on any scale that we expect things to vary. We do this by obtaining precise and accurate position measurements of point sources while moving the sources in the field of view. So the assumption again is that the sources have moved between observations hours apart, and therefore their relative position, the fact that the relative position remains the same provides very detailed constraints on the geometric distortion solution, because you're looking through different parts of the optical system in each observation. The requirement that we have is to a large field, about twice the field of view in each direction, with a high source density, where the large field is necessary because then you can cover from corner to corner the field of view, and with the same sources. And then you also additionally need small dithers to sample relevant scales. Also, this is a special requirement for astrometry, you need different roll angles to measure and constrain the skew, because if you obtain observations a single roll angle, then the skew is essentially degenerate. And so the solution needs to, the field has to be in the CVZ so you can observe at different roll angles. Now, you're not starting from scratch. You know a lot about positional sources. So Gaia will provide very accurate positions, better, more accurate than we need for bright sources. However, the density of Gaia sources is not high enough to be able to characterize the distortion of the instrument on a sufficiently dense grid. So basically, the combination of Gaia sources that provide general constraints and absolute constraints and the size, for example, the scale, and of this very high density field that you observe multiple pointings to match the positions will provide the solution. The large Riemann field that we have identified for photometry is also ideal for astrometry. Again, the source distribution is close to uniform. Number and brightness of sources allow reaching signals of 100 in 1 minute or less. And there are not very many excessively bright stars that might cause holes in solution. So this is another view of the same field, this on a slightly smaller scale. But also, this shows that this field also includes the JWST astrometric calibration field, which is much, much smaller, of course, but was used to obtain a JWST astrometric solution. So it will also provide a match in terms of both astrometric and photometric calibration to JWST, because we have plenty of data on that region. And again, as I mentioned before, the actual orientation of the field will depend on the time of year and therefore the launch date for commissioning. So how do we do the observations? Well, astrometry requires extensive dithering. So basically, we use a set of about 100 dithers to provide the required solution quality. Andrea Bellini has done a very thorough, exhaustive analysis of the solution process, and he has come up with this plan that has the small dither package, where you basically move the pointing, the reference pointing on a 7x7 grid over the detector. And then large dithers, where you move the pointing on a 9x5 grid over the whole field of view. So which basically you mix observations, different detectors. Therefore, you help constrain the relative position of the detectors, which otherwise would be degenerate in the previous one. Sorry. And in addition, you have the roll dithers. Only 6 of them are sufficient. I'm sorry. Apologies. To constrain the skew term. Now, this part, the roll dithers, cannot be done at the same time as the others because they require the time to go by, so we can change the roll angle of the telescope. But all the rest can be done quickly, and the time required to do these 2 sets of dithers in all filters and for all exposures is about 24 hours, including the overheads that we currently estimate. And these include all the dithers that will be needed for photometric observations as well. So basically, this set of observations will do both the astrometry and the photometry for the LMC field. Okay, that was that for astrometry. Are there any questions? If not, am I leaving enough time? Well, okay.
Just pause another second or two. Looks like we have actually a question Rebecca, did you mean to raise your hand there?
No, I was trying to do a reaction of a thumbs up. Sorry, my bad.
No worries at all.
We'll
And
take
also,
thumbs up
folks
any
are,
time of the day.
yeah, and of course, if you remember a question later, we can come back to it at the very end, or if you have a question, put it in the chat as well.
Thanks. By the way, I don't see the chat right now because of I'm displaying.
No worries.
Okay, so let me go to spectroscopy. Again, I'm not the expert on spectroscopy, but if there are any questions, there are experts in the audience. So the goals, the main goals of the spectroscopy touchstone field observations is to measure the large-scale chromatic illumination patterns, basically the relative flux calibration as a function of wavelength over the field of view of the instrument, to monitor the variations throughput over the full field of view as a function of time, and to determine and confirm the blue edge and wavelength solutions over the field of view to measure and monitor variations in the wavelength calibration. So these are the main reasons. For this purpose, the recommended targets are the Euclid deep fields, north or south, probably north, for the relative flux calibration, the southern beehive for the Grism wavelength calibration and monitoring, and the planetary nebula SMC SMP 20 for prism wavelength calibration and monitoring. But there are also a few alternate fields that have been identified as backups, just in case there are issues are found with any of these. So let me go in order. For relative flux, the primary field is Euclid deep field north. It has a somewhat lower density than would be ideal, as I mentioned also for the photometry part. However, in the case of spectroscopy, there is a concern with trace contamination. Basically, the traces, at least for the Grism, are very long and they could overlap. And so having a lower density of sources and doing more dithers may be desirable. So the Euclid deep fields are actually very large, 20 square degrees, and they're in the Roman CVZ. This is the Euclid deep field north, and the Euclid field of view compared to the Roman field of view on the right. So we can choose essentially any location in the Euclid deep field north, and they will be observed. Each of them will be observed by Euclid over 40 visits each, and so will provide a lot of starting information about the source in the field. So Roman observations, again, spectroscopic observations in multiple data positions will provide the relative flux calibration by observing the same source at different locations in the field of view, so you know how much the response is changing as you change the location of the source, and then you can correct for that. A star with H-band AB magnitude of 17 can reach about 100 signal noise, about 100 and 300 seconds per resolution element in the prism, and about 50 per resolution element in the Grism. So you have to average over a few resolution elements to achieve 100. And then if you do about 20 different dithers, you will provide coverage of the field of view in a solution at the required level for about 15 by 15 arcsecond regions. So we divided the detector in about 28 by 28 regions, and you can compare them, one to one another. To obtain these observations, it takes about 3.5 hours per visit. It says including both principles. That's for 1 or 2, so it's 7 hours total. My bad about that. And these fields, both the north and the south, include some white dwarfs that have HST observations. So for these, they would provide a path to absolute flux calibration if we make sure they include one of these white dwarfs in the subfield. For the Grism wavelength, the primary field is the southern beehive, which is in a rich open cluster, which is in the Roman southern CVZ, obviously. This has a very high density of young bright stars, very bright stars, over a large fraction of the Roman field of view. You can see it in this image. It doesn't cover the whole field, so we'll need some dithering, but it's a fairly good fraction. And for these stars, they expected to have significant absorption lines. In particular, Pascha and Beta is in the middle of the range that that the GRISM cares about. And the GRISM resolution is sufficient to actually measure these spectral lines accurately. And so basically we use those lines for these stars to be able to verify and confirm the wavelength calibration. There are about 100 stars per detector to a Gaia R band magnitude of 17. You may want multiple rolls to help avoid contamination, but again, those additional rolls will have to be obtained at a later time. Current estimate is that about 13% of the pixels will have contributions from multiple stars up to 2 magnitudes fainter than our faint magnitude limit. So there are a few concerns. As you can see, there are a couple of stars. So I think the brightest of those is 4th magnitude, so it's very bright. And so there is potentially an issue with the bright stars in the field. It's going to be somewhat difficult to avoid them completely. So it's not completely clear that you can do all you want in this area. And so Greg and collaborators have looked at possible backups, one of which is NGC 6811, an open cluster in the Kepler survey field. There are several in that field, but this one has a somewhat larger extent, but still has good density of stars. It only covers 3 detectors. So if we were to go to this cluster, it would require more pointings. The spectral contamination is lower, however. So there are potential advantages. It's also possible, it's been suggested to use galaxies as wavelength references, either by using many of the HST GRIN spectra and ground-based spectra available in well-studied cosmology fields like Cosmos, Extended Growth Strip, Goods North, and others, or by using emission line galaxies from either Roman surveys or ground observations. If those options need to be pursued, then it will be more work will be needed to figure out the details. And sorry, at the bottom I should have mentioned is the color magnitude diagram and luminosity function for the stars in the southerly high field, and you can see how well developed the main sequence of the cluster is. But of course, there are also stars that are just overlapping in the field. Okay, finally, prism wavelength. The prism wavelength calibration is a little more difficult. You cannot use stellar lines, most likely because they're unlikely to provide good wavelength measurements at that resolution. The target has been the primary way to do calibration, for example, for JWST and HST GRISM, has been using planetary nebulae. So a planetary nebula with multiple emission lines, a compact planetary nebula with multiple emission lines is being selected. The best candidate was identified by the Euclid team. In fact, they tried over a dozen of different planetary nebulae. This was the only one that turned out to be suitable after ground-based VLT observations at high resolution, and after considering the type of crowding that might be problematic for these observations. This particular planetary nebula is about 0.2 arc seconds in HST images, so it's small enough to be acceptable. For this particular program, because it's a single target as opposed to the GRISM where you have many targets, you will need to observe the planetary nebula in multiple positions. The Euclid experience suggests that 3 positions per detector are sufficient, and with 400 seconds per exposure, that requires about a little over 5 hours plus potentially overheads. I'm not sure exactly how carefully the overheads have been worked out for this case, but that's per execution. So that would provide enough information to obtain a wavelength solution with multiple lines, multiple emission lines for the planetary nebula. Other alternatives would be the planetary nebula used for JWST, or some of the fainter planetary nebula in the atlas that Euclid collaboration produced, some of which they excluded just because they were not bright enough. But Roman is bigger, so it may be able to go fainter, maybe at a small cost in observing time. And I think this concludes what I wanted to say generally about the touchstone fields. So to summarize, at this point, we have identified good target fields for a number of key WFI, well field imagery calibration activities. These targets are accessible throughout the mission, regardless of launch date. They will be accessible in commissioning. So the first observations will likely take place during commissioning, and follow-up will be decided by the commissioning steering committee, depending on whether stability and calibration quality need to be verified quickly or can wait until later. In some cases, additional observations, different roll angles may need to take place after commission is concluded, simply because you either want to disentangle a contamination for spectra, or you need different roll angles for skew constraint for astrometry. And just in case they are needed, several backup options have been identified, but some of those will require further analysis. And this concludes what I wanted to say today. So thank you very much for listening, and please ask any questions.
All right, let's get some clapping hands emojis. You can click on the little smiley face at the bottom of your screen and click on the clapping hands. Thanks for that great presentation. Now we have time for some questions. You can do it again in one of two ways. You can raise your hand, which is that hand raise icon, high five icon to the left of the smiley face, and I'll call on you to unmute yourself, or you can write your question in the chat and I will read it out loud. So we'll pause here for a few seconds to see if we have any questions. And Casey is asking in the chat, how long after commissioning is required to cover all the roll angles needed for the astrometric calibration?
Well, in principle, if you want to obtain 6 angles separated by 30 degrees, or sorry, by 60 degrees, then you need a year, or a year minus 2 months. In practice, things aren't quite that bad, because the solution is already constrained. The skew solution is already constrained to some extent by the Gaia positions. So it is possible that you can obtain a solution, or in fact, you will be able to obtain a solution with the skew constraint, even without the additional roll observations. But the additional roll observations will provide a stronger constraint on skew. So I think it will be a year before we get to the final solution for that purpose. But we'll get a very good solution without that. I just, you want to conclude it. Does that answer your question?
Yes, Casey says thanks in the chat.
I'm sorry, I can't see the chat.
Yeah, no worries. All right, well, folks are thinking about other questions. I did have one quick question, actually two. The first one is, the Prism needs the nebula to do its calibrations, but why not also sort of double dip and use that for the GRISM? Is it just a question of efficiency for observations?
Well, so it's possible, of course, to do that. In the case of the GRISM, the quality of the measurement of the wavelength calibration needs to be much higher. The precision has to be, in terms of the uncertainty, the better. We have a requirement that's, I believe it's 10 to the minus 3 in relative wavelength calibration, which is decomposed to a tighter requirement, because that information goes into the high latitude imaging survey. Spectroscopic survey, my bad. And so the quality of the measurements that can be obtained with the sort of beehive, because of the higher density of sources, more quickly is better. At least that's my understanding. But perhaps, I don't know if this is the case where Greg might want to chime in.
I think you answered it pretty well. I think the only thing to take away is, like, during commissioning, we will do planetary nebula for both the Prism and the GRISM. And the purpose of this whole exercise is to monitor the wavelength solution, to make sure that the wavelength solution isn't changing over time. So this is why we have these touchstone fields.
Thank you.
That actually ties in very nicely to my next question. How often will you be returning to these touchstone fields, and are you going to be monitoring all the different sort of calibrations or monitoring activities here, and are they all sort of the same cadence?
So the answer to that is rather complex. There are a lot of monitoring activities that happen simply as a result of the surveys. So for example, photometric stability is verified to a large extent by simply doing an Oberkahl type analysis on the high latitude imaging survey during that observation, or during the galactic bulge time domain survey using those observations. However, it felt important that on a regular basis would go to a field that is well known and well understood and do a direct comparison. In a case where the field is not excessively crowded. So this, if you will, the temporal monitoring done with the Touchstone Fields is supplemental to what already happens during the mission as a result of the type of observations the mission will do. We nominally put in every 3 months for photometry, but that may be, it may be too frequently, or maybe not frequent enough. Depends on what we see in flight. But this is not the only way that we have to see if there are variations. So that's very important to keep in mind. I think the current thinking is to repeat at least once one of these two fields during commissioning. So during the first 30 days. That's as a sort of a safety measure to make sure that we are in the right place. But that I think has not been decided yet. It's the current thinking. For spectroscopy, the ability to do the internal comparison is not quite as extensive. So the plan, I think the nominal plan is to repeat a subset of the observations every month. So 12 times a year. But again, these are current thinking guesses based on, not having seen the mission in flight. When we see the mission in flight, we'll have a better feel for how stable things are.
Great, thank you. All right, any other questions? We have a few more minutes. Jeff, go ahead.
Actually, this is a bit of a follow-up to Rob's last question, particularly on astrometry. Has anyone been thinking about how well we can monitor the astrometric solution just by tracking the Gaia stars in every image or select subsets of images? Or do you really need something taken in a more systematic fashion?
I promise I did not plant that question, Jeff. It is absolutely the case. We plan to monitor the residuals. We plan to do for every observation. There will be a step of the pipeline that will determine the position, the pointing on the basis of the Gaia stars in that image. And we plan to look at the residuals. And if there is anything strange in the residuals, we should see it right away. So this is absolutely something that can be and will be monitored.
So actually, I do have an ulterior motive, because although I'm still working with some of the optics people here, it could be that will be a more sensitive diagnostic of dry out of the telescope structure than just monitoring the focus.
Oh, interesting.
So
So
it may be useful for
light
many
scale
things.
change.
Correct.
Good to know. I see now that there's a question. Yes, Roman data are public and will be processed and released, to the archive. Now, whether there will be some special, media type releases, I do not know. That's very early to know. But all the images, all the Roman data will be public.
Excellent. All right, we have time for one more question. If someone has one more question, we also just start randomly calling on project science folks too.
Let me just make a comment on the last question. I
Sure.
think Roman will have an enormous potential for cool images, and I hope we'll take full advantage of that for the community and for the public at large.
All right, I'm not seeing any questions in the chat. I'm not seeing any raised hands at all. So let's get 2 minutes of our life back. That would be nice. Let's all thank our speakers for today. Thank you everyone for calling in today. Thanks for the excellent presentations. And we will catch up again next month at the next Roman Community Forum. Thank you everyone for calling in. Roman, and we'll chat with you all very soon. Thanks everyone.
Thank you.